All right, guys, so in today's video, we're going to be talking about residuals and how they're useful for us when doing linear regression for a set of data. So first of all, definition for a residual, it is the difference between an observed value and the predicted value of a particular response variable. So in order to calculate a residual, you'll take your observed value minus your expected value. In other words, you'll take y minus y hat. When you interpret a residual, a negative residual means that the prediction was an overestimate. Now, that might be counterintuitive because you would think negative means it would be below, but remember the order that we're subtracting these in, we're taking observed minus expected. So if we get a negative difference, that means that the expected value was greater than the observed value, which would mean that our prediction was an overestimate. And in a similar way, a positive residual would indicate that the prediction was an underestimate. That would be because our expected value was less than our observed value. Okay, so to give you an example of this, let's go ahead and calculate and interpret a residual for a can of soda that was tapped for 4 seconds and had 260 milliliters of soda remaining from that previous section. So I've gone ahead and copied over the equation from that section. We had that soda hat was equal to 248.6 plus 2.63 multiplied by the tapping time. So first of all, let's figure out what our predicted value would be for a can of soda that was tapped for 4 seconds. So we would say that soda hat would be equal to 248.6 plus 2.63 multiplied by that tapping time of 4. So here would be our predicted value. If I put those into my calculator over here, I'll find out that my predicted value is 259.12. Now, the actual can of soda itself had 260 milliliters of soda remaining, and my prediction was less than that. So it looks like my prediction is an underestimate, and so let's go ahead and use a residual to show that. So for my residual, I'm going to take my observed value minus my predicted. So I'm going to take 260 minus that 259.12. So my residual for this particular data point would be equal to 0.88. So in terms of my interpretation, I need to make sure I do that in context and also mention the fact that we underestimated our amount of soda. So we're going to say that we underestimated the amount of soda left in the can by 0.88 milliliters, which was pretty darn close. So whenever we interpret, we are looking for how far away our expected value was from the actual value from our data set. Let's go ahead and take a look at another example of this in a slightly different context. For our example, we're going to look at the amount of carbs and fat in McDonald's beef sandwiches. So we're thinking cheeseburgers, hamburgers, the Big Mac, quarter pounder, all of those types of burgers. First of all, how can we determine the best regression line for a set of data? We typically use 2 things. One that we're going to be talking about today are the residuals, and we'll talk about how to use those. The other is we will start to talk about a couple of other variables. We'll talk about what's called the coefficient of determination, which is r squared. We'll end up doing that in the next section, as well as S, which is the standard deviation of our residuals. And again, we'll talk about that in a future section. So for today, we're going to focus on how we can use residuals to figure out our best regression line for a set of data. Now, is our least squares regression line resistant to outliers? The answer is no. In the same way that R, which was our correlation coefficient, was impacted by outliers and other influential points, our least squares regression line is also going to be affected by those outliers. So let's go ahead and calculate our equation of our least squares regression line. We're going to do that using our calculator. There are ways to do this by hand. There are some formulas that we could use that are helpful for us. All those formulas are on our formula card. But for today, to make it easy, we're just going to use our calculator. It mentions to make sure to define our variables. So if we want to use variables like x and y, we need to make sure we define what those variables are. So let's go ahead and do that for this particular example. First, we need to figure out which of our variables is explanatory and which one is a response variable. In this case, I'm going to say that the carbs are most likely the explanatory variable. The amount of fat then is the response variable. In other words, the amount of fat in the sandwich depends on the number of carbs that are in it. So for my particular equation, what I'm going to use is I'm going to use y as my response variable. And so y hat is going to be what that will be in my equation. That's going to be then the predicted amount of fat for the sandwiches in grams. So x is going to be my explanatory variable. That's going to be the amount of carbs, not predicted amount, but the actual number of carbs of each sandwich, which was also measured in grams. So let's figure out how to put this into our calculator. The first thing is we need to put all of our data into our calculator. So if we go into stat, we'll choose the option for edit, and let's go ahead and get our data into list 1 and list 2. For the sake of time, I've already got those in there. So if you need to, pause the video and then go ahead and play it when you've got your data in. So first, let's go ahead and calculate our least squares regression line. So we're going to quit out of the stat menu, go back into it, over to stat, and then I'm going to choose option 4 for linear regression in AX plus B form. I'm going to go ahead and select that, and it should automatically have X list as list 1, Y list as list 2. If you need to change either of those, if your data is in a different list, make sure and do that. Once again, we're not using a frequency list, so you can go ahead and leave that blank. And then let's go ahead and store our regression equation. A reminder with how to do that, we're going to go into the vars menu of our calculator, over to y vars, so for y variables. We're dealing with a function here, and we're going to choose the first option for y1. Go ahead and hit calculate, and we should have our regression equation. If you do not see r or r squared, that is where you need to go into the mode menu of your calculator and make sure that your stat diagnostics are turned on. If you need help with how to do that, go back to that previous video that we had for correlation in the last section. Okay, so to write my equation now, I'm going to say that y hat is equal to a, which was 1.71. I'm going to go to just the hundredths place to write it down, multiplied by x, which was the amount of carbs, minus my y-intercept of 40.20, again rounding to 2 decimal places. Now, another way that we could write this, if we don't want to have to define our variables, we could have also said that fat hat is equal to 1.71 multiplied by your number of carbs, and then minus 40.20. So when you're defining your variables, you can do that one of two ways. If you want to use x and y, make sure to say what they represent. If not, make sure to use the actual context when you write your equation. Now that we have our equation, let's go ahead and do a couple things with it. First, on the next page, let's go ahead and interpret the slope of our regression line. So the slope here was 1.71. To write that as a fraction or as a ratio, we would put 1.71 over 1. And so remember, for slope, we have to interpret this in context of both variables. So what we would say is that for each additional 1 gram in carbs, we expect the amount of fat to increase by the 1.71 grams. Next, let's go ahead and interpret our y-intercept. So the y-intercept in this case was negative 40.2. So we would say that we would expect that a sandwich with 0 grams of carbs to have negative 40.2 grams of fat. Now, let's think about whether or not we can actually say that. Is it possible to have a negative amount of fat for a sandwich? And the answer is no. Really, this interpretation is not reasonable. And so if that's the case, if I ask you to interpret it, go ahead and interpret it, but go ahead and say something along the lines of, it's not reasonable based on the context that we were given. Okay, next for part E, let's go ahead and calculate and interpret the residual for a Big Mac, which had 45 grams of carbs and 29 grams of fat. So 49 grams of carbs, there's going to be what we use as our input. That's going to be what we put in as our X value into our equation. So we would say that the predicted amount of fat would be equal to 1.71 multiplied by 45 and then minus that 40.2. So let's see what we come up with. 1.71 multiplied by that amount minus the 40.2 from previous is going to be equal to 36.75. Compared to the 29 grams that we expected, clearly that was an overestimate. We overestimated it. Let's figure out by how much, and that's where we'll calculate our residual. So for the residual, we were expecting there to be we know that there were 29 grams of fat. So find our residual. We're going to take that 29 grams of fat minus the 36.75 that was predicted is going to be a difference of negative 7.75 for our amount in our example. So in other words, what we would have to say is that we, in this case, overestimated the amount of fat by 7.75 grams. Now, why was that? Well, for anyone that knows about the Big Mac sandwich, the Big Mac has an extra bun, an extra kind of bottom bun in the middle of it. So there's actually a top bun, a bottom bun, and actually a middle bun. So a Big Mac has more carbs in it than other sandwiches, but does not have an extra patty in there. It still has 2 patties in there, but it does not have a third one to match the 3 buns. And so that would most likely be the reason why we overestimate. Now, how do we know whether this model is appropriate or not? Let's go ahead and talk about that. So a residual plot we can use to help determine whether or not our model was appropriate for our set of data. So what a residual plot is essentially a scatter plot that shows your residuals against the explanatory variable. In other words, the residuals in our example from up above graphed against the number of carbs in each sandwich. The purpose of a residual plot then is to determine whether or not that model is appropriate. And to do that, we need to look at whether or not there is any apparent pattern. If there isn't a pattern, meaning that all the points vary from our line of best fit by about the same amount or are equally kind of spaced around, then that tells us our linear model was appropriate. We don't want for all of our points to be below our residual plot or our line of best fit, because then that would mean that our line of best fit was over predicting the amount. We also don't want for them to all be above our line of best fit, because then we would say that it was all going to be underestimates for the actual amounts. We want it to go almost exactly through the middle of it and having equal number of points roughly above and below. So let's go ahead and make that using our graphing calculator. First, let's just go ahead and look and see what our scatter plot looks like. So if you go into the stat plot menu of your calculator, we're going to go ahead and turn plot number 1 on. We're going to go ahead and make sure that that is a scatter plot option. And then for X list and Y list, make sure those are list 1 and list 2. Now, in the Y equals screen, if you went ahead and stored it along with me, you should go ahead and see your line of best fit already there. If not, this is where you need to type that line of best fit in before you go ahead and hit graph. Remember, to graph it, hit zoom 9 to be able to zoom in specifically on our data, and here is our line of best fit. So it looks like our line of best fit did a pretty good job of going through the middle of our data. We've got roughly the same number of data points above and below our line, but we need to now look at our residuals for our data set and see how those compare. So let's go back into our stat menu and let's go ahead and calculate our residuals for all of our data. So we're going to hit edit here, and then let's go over to list 3. And for list 3, we're going to calculate the residuals for all of our data. To do that, there's actually a residual list that we can use. So we don't have to necessarily do this by hand. So go up to list 3, and then above the stat button, you'll see the option for list. If you hit second stat, then it will pull open a list menu for you. Now, here's where you have the lists for most of our common lists that we'll use, list 1, list 2, and so on. You'll see option 7 is a contributions list. So if you ever needed to do that separately, you could. And then if you scroll down, there'll be another option below that, which is called resid, which stands for residuals. So what we're telling our calculator to do is for list 3 to calculate a list of residuals for our data. And if we press enter, we'll find the residuals for all of those data points that we have. Now, if that did not work, make sure that you've done your linear regression. And by the way, you need to do that first before calculating your residuals. So anytime you want to calculate residuals using your calculator, you must have first done a linear regression for it. So let's go ahead now and graph our residuals. So we're going to go back into our stat plots menu. We're going to go back into plot number 1, and we're going to change our Y list to be our list of residuals, which remember we put into list 3. And then for the sake of not having a line in there, let's go back into our Y equals screen. And if you want to clear it, you can. If not, you can just go over to the equal sign and turn Y1 off. That way you don't have this line of best fit going through all of your residuals. And then what we should be able to do is go back to zoom 9 for zoom stat and see a residual plot of our data. So here is a graph of all of our residuals plotted against our explanatory variable, which in this case was again the number of carbs. Looking at our residual plot, again, it looks like there are roughly the same number of points above and below our axis. While some of the points are a little bit further away, there's not any points that are really far away. There's also not any sort of pattern here in our residual plot. So in terms of constructing and interpreting it, here is our construction of it. To interpret it, we would say that in this case, a linear model appears to be appropriate because of the fact that we don't have any apparent pattern in our residual plot. By the way, if you don't want to have to make a whole list for residuals, if you just want to go ahead and plot them, you could also do the same thing in the stat plot menu. So in your stat plot menu, if you go to your stat plots for Y list, if you don't have your residuals already in a list, you can go ahead and do that here. So for Y list, you could also go second stat for list and choose residuals as your Y list. You'll get actually the exact same graph as before. That just saves you the extra step of having to put them into list 3, but oftentimes it's helpful to have those residuals in case you need them. All right, guys, so now we know how to begin assessing whether a linear model is appropriate by using a residual plot. In the next section, we'll start to talk about a couple of other things that we can use. Namely, we'll talk about the standard deviation of our residuals, which we call S, as well as the coefficient of determination, which is what's called R squared. Until then, have a good rest of your day.